Hello, welcome back to the channel and this continuation of this series on shapes, and today we're going to be looking at polygons. Polygons are the name given to any multi-sided shape, but you typically come across the term when the number of sides of that shape is greater than 4, because below that you normally have triangles, squares, rhombuses, rectangles that we've already looked at in this series. So today we're going to look at the properties of pentagons and hexagons, and the principle that I'm going to apply to these will then apply to higher order shapes. So you can go through heptagons, octagons, nonagons, decagons, and then for the whole range of polygons. In the previous videos in this series, I've been mainly concentrating on finding the formula for areas. I'm not going to do that today because before I do that, I need to make another video which will be released next week, which is on calculating the heights of triangles. So today I'm just going to look at some of the angular properties of these two shapes and how to calculate them. Throughout this video, what I've been trying to impress is that you don't need to remember formally. It's better if you can actually derive them and come up with them yourself, and the way I've been doing that is by splitting the shapes down into things that we already know. So in the simplest form, those are generally triangles, and that's what I'm going to apply to this shape here. So we're going to start off with this pentagon. So the properties of a normal pentagon has 5 sides, all of equal length. Let's call them all A. Now if we want to try and break this shape down, so let's say if we did want to calculate the area, which we will do eventually, but also just calculating the internal angles. If we start off in the middle of the pentagon, and we draw triangles going to each of the corners of the pentagon, we're going to end up with 5 equal sized triangles. And this area in the circle, or this point in the circle, or this point in the pentagon has basically a circle going around there. So that has 360 degrees. Which means if we start off with that 360 degrees and we divide it by the number of triangles, which is 5, we end up with 72 degrees. And therefore this is the angle here. So the top angle of these triangles is 72 degrees. These other angles down here are going to be equal. So this is actually formed an isosceles triangle. So we have 5 isosceles triangles here. And therefore the remaining 180 degrees less that 72 has to be split between these two. So if we start off with 180 degrees minus that 72, that's equal to 108 degrees. If we divide that now by 2, we'll come up with 54 degrees. And therefore this is these angles here. Now if we want to calculate one of the internal angles, we just take it that we have another triangle here with 54 degrees. We can add these two together, so the internal angle is 108 degrees. Of course, we could have just come from that by just taking that 72 away from 180. And we have 5 of these internal angles. So the total sum of the internal angles is 108 times by 5, which is the same as 54 times by 10, which is 540 degrees. So that's the sum of the internal angles of pentagons. So that's one of the properties of a pentagon. If we do the same with a hexagon now, and we divide this into equal triangles, we are going to end up with 6 of them. So we can do exactly the same process to find out what this angle is and what these two angles are. So let's start off with the 360 divided by this time 6, because we've divided into 6 triangles. That will give 60 degrees. Now, in our video on triangles, we saw that equilateral triangles have all angles equal to 60 degrees. And we know these two must be equal, and therefore this must be equal to this top one as well. So these are all equal to 60 degrees. So this time we have an six equilateral triangles in there, and the angle of each triangle is 60 degrees, which means that the internal angle of a hexagon is going to be equal to 120 degrees. You've got 60 degrees from this contributing from this triangle, and a 60 degrees being contributed from that angle. Now, if we do 120 multiplied by 6, we end up with a total internal angle of 720 degrees. So that's one of the properties of the hexagon, that it has equal sides, and also that the sum of the internal angles is equal to 720 degrees. So before we finish this video, I just want you to draw your attention to this. So one of the things about maths is looking, and science as a whole, is looking at trends. So if we start off with a triangle, the sum of the internal angles is 180 degrees. A quadrangle, such as a square, has 360 degrees. The pentagon had 540 degrees. The hexagon had 720 degrees. So what is there a trend between this? So you can see that each number actually increases by 180 degrees, which means if we had a 7-sided shape, we just have to add 180 degrees onto that, which would give you 900 degrees. An octagon, which is the next one up, would have 180 degrees added onto that, which is 1080 degrees. So you can start seeing the trend here. So once we end up seeing this trend, we can start trying to think of a formula for this. So there's numerous ways of deriving a formula, or coming up with a formula, but the way that I would think about this is if you always started off with your triangle, which is 180 degrees, and to that we're going to add a number, and the number will be the extra number of sides, so we'll call y the number of sides, so y equals, actually we'll call it number of sides of the shape, so number of sides minus 3, because we have to take off the number of sides for that triangle, and we're going to multiply that by 180 degrees. And now if we can test this formula, so if we start off with this square, we start off with 180 plus y is number of sides, which is 4, minus 3, which is 1, plus 180, which will give you 360. If we take, say, the hexagon, then y is number of sides, which is 6, minus the number of sides of the triangle, which is another 3. So 3 times 180 is 540. Add that to the 180 equals 720. So you can see that this formula seems to run true for that. So this is something that I want to try and press on you through these videos. It's not just about learning equations and just then applying them, but actually thinking about the shapes, thinking how those equations are formed by breaking it down into things that you know. Anyway, I hope you enjoyed this video and find it useful, and I'll see you again next time when we look at how to calculate the heights of triangles.